So another method of heat transfer is convection. And you may have heard of convection if you've come across a convection oven. I have one of those actually in my home. I love it because it cooks things a little bit faster and more evenly. So let's talk about what convection is and why that might work. So convection is, let me move my face out of the way. Convection is the transfer of heat by the displacement of groups of high energy molecules. All right. So the thing is that convection only happens in liquid and gases. So we talked previously about conduction, which happens in solids. Convection only happens in liquids and gases. So what are we talking about happening here? Here, the heat is going to transfer by molecules moving energy from one group to another in a liquid or a gas. And they do that by being moved around. So if we take a look at over here at the pictures in the corner, the best one probably to look at actually is the pot down here. So this is a pot of water that we would want to get boiling. And we've applied heat at the bottom. And you can see the little arrows pointing in different directions. This is the displacement part. So the molecules are being displaced, being moved around because they are getting energized. So a lot of the arrows are going up because those molecules have lots of energy. And so they are moving more. And when they move, they bump around and they end up pushing the lower energy molecules down. And so this causes what we call convection currents. They roll around. So if you watch a pot of water long enough, you'll start to see it kind of looks like what we call a rolling boil. And that's why you're getting a convection current. That's what you're seeing in this picture here as well. Because you've probably heard hot air rises. And that's because, and that's why you see all of these arrows going up, and then the cold air sinks. The colder air that's up at the top is going back down, and it keeps getting warmed up because this is actually allowing it to be warmed up through a little window. So what's going on? So here is what cold air looks like. The molecules are very close to each other, and these little lines are showing how much energy they have. So not a lot of energy, really, and they're really close together. They'll run into each other, but they're not going to run into each other very hard. Here is what hot air molecules look like. Not a lot of them compared to cold air, so they are less dense, less closely packed together, and they have a lot more energy. And so this is actually why hot air rises. Hot air rises because it's less dense. It's basically lighter in a way. And so the hot air is going to rise up because it's much lighter than the cold air. And then it's going to end up, because it goes up, it's going to displace or push out the cold air, push the cold air down, and then the heat source is going to warm those cold air molecules up and repeat the whole process over. So, oh, there we go. What does warm air do? Warm air rises. And because these molecules are spaced out more, they have more energy and are running into each other. All right, so this comes into the convection currents that I mentioned in that pot. So these are bigger versions of that. So these are just the circulation patterns that form because of rising warm air and sinking cold air. So they can happen on big scales, like out over a body of water, like a pond or a lake. And the reason why they happen out there is because during the day, you get hot air rising off of the land because the land heats up faster than the water. And then the cool air sinks out over the land and gets the convection current going that way. So hot air rising over the land, cool air sinking over the water. This is why during the day, the breeze by a lake is going to blow inland. And then at night, it reverses, because at night, the land is going to be cooler than the lake and the water will be warmer. And so the water is warmer, it's going to warm up the air, warm air rises and pushes the air, and cool air sinks out over the land. And so at night near a lake, the air is going to be pushed offshore. And you get the same thing in a house, right? When you have the heat going, the warmest place in the room is up near the ceiling, and the coldest place is down near the floor. So when you have heat going, you're ending up creating these convection currents. That's why often a lot of houses end up putting in ceiling fans, not just to move cool air in the summer, but also to push the warm air down during the winter. So the last thing with convection that I've got here is a cool little experiment, cooling by expansion. So this is another web link I will put in the lesson, and I would like you to give it a try, because what happens is when air expands, it cools off. And this little video is going to give you a little demonstration to try that off. So please give that a try. So our last way to transfer heat is via radiation. So we've got conduction with solids, we've got convection with liquids and gases, and then we have radiation. So radiation, or radiant energy, is energy that's associated with electromagnetic waves. So over here along the side, this is the electromagnetic spectrum. I mentioned that in an earlier video. So the electromagnetic spectrum that we're used to is this part right here, the visible part of the spectrum, the Roy G. Biv. But there's more to it than that. So you've got ultraviolet and infrared. Infrared, again, is heat. But you've also got things like microwaves, radio waves, X-rays, gamma rays. All of these belong on the electromagnetic spectrum, and they all contain energy. These guys can operate in a vacuum. That's how we get the energy from the sun to our planet. If they didn't operate in a vacuum, we wouldn't get any of that energy. And the thing is that all objects emit and absorb radiation. So we absorb radiation from our surroundings. So we absorb infrared and light and so forth. And we also emit radiation. Now, humans, for example, we emit infrared. We emit heat. We don't emit visible light or anything like that, but we do emit infrared. And with radiation, the transfer will occur as long as there is a temperature difference between the object and the surroundings. So the surroundings that contain the radiant energy. So you're familiar with this kind of idea because you've been around objects with color in them. So the ability of a material to absorb and radiate thermal energy is indicated by its color. So think about these two pictures. So we've got a picture that's painted black and a picture that is painted white. Which one of these pictures will warm up faster if we set them outside? Yeah, the black one, right? I mean, we know this. If we've probably done something like this before. You probably set something outside that was dark colored, and when you went back and picked it up, it was hot. We know that wearing a dark colored t-shirt out in the sun is going to make you feel hot, but if you wear a light colored t-shirt out in the sun, it will make you feel cooler. And this is why. It has to do with the absorption of radiant energy. So when you wear that dark colored t-shirt out in the sun, it's going to absorb the visible light rays as well as things like some ultraviolet and some infrared. So think about things like walking barefoot. If you wanted to walk barefoot somewhere, would you rather walk on concrete or asphalt? it's the same idea. Asphalt is going to absorb and radiate more of that radiant energy than concrete will, right? Concrete will absorb it, but it's going to radiate it pretty quickly. It's not going to hold on to it like asphalt will. All right, that's the end of methods of heat transfer. So the last sections are phase change and thermodynamics.